Hello, this is Silvia Mazzoni. I'm going to talk about ground motion variability in terms of scaling and mean spectrum modification. The first thing you got to do is you got to look at your prescriptive criteria. What are you working with? I'm going to focus on the very latest, which is the ASC 716. In the old days, there was a separation between far field and near field for the scaling, but now it's about rotating of the records. So in the far field, you have to have at least 11 ground motions, and the objective of the scaling or the modification is that the average of the maximum component, whether it's max component or the rod D100, of these 11 ground motions must be greater than or equal to a factor of your design spectrum. It really depends on whether you modify your records or not, what this factor is. And you'll see that in a later bullet point. And this has to be done within a certain period range. So you don't do it over the entire period range of your ground motions, but it becomes very specific and associated with the specific period of your structure. For near fault sites, in the records that you have selected, you must be able to represent pulse characteristics and other characteristics that are representative of your site. And those are really dependent on magnitude and distance from the fault. And so you got to apply the records in the fault normal and fault parallel components of these orientations. What's your target spectrum? Well, you can do a couple of different things. You can use your uniform hazard spectrum, which becomes your uniform risk spectrum, or based on that uniform risk spectrum, you can compute a conditional mean spectrum. And with the conditional mean spectrum, you got to make sure that you meet certain criteria, so you may have to do this for a number of conditioning periods, at least 2. Typically, it's 3 is really the reasonable number, and there's additional criteria on the selection of these periods. And what I'm going to be talking about applies to whether you're doing an UHS or URS target spectrum or your CMS. What are the 3 different methods of modification that you can do? Well, the basic one is amplitude scaling. In amplitude scaling, you're not modifying any of the frequency content of your ground motions. You're literally just putting a scale factor in front of your record. In this case, your factor that you apply here in front of your design spectrum is 0.9. So it gives you a little bit of latitude when you're just doing amplitude scaling, that not all your spectra have to be above the target spectrum, but just above 90% of your target spectrum. So people call that a 10% discount. From ASC 710, it doesn't apply anymore, so we can cross out this line right here. There's also tight spectral matching, which is what most people just call, spectral matching, where you modify the record such that the response spectrum of each component, but you're really trying to modify the record such that the max component of each record is equal to the target spectrum. Very important, and this is why I left it to be edited, because I want to make sure that you see the transition as things evolve. You can do the old-fashioned 1D spectral matching, where you have to modify pretty much each component, or now there's a new method where you modify the record pairs together such that the maximum component of each record pair matches the target spectrum. So with what I'm doing, it's really kind of the same result in the end. But remember, what you're doing is you're modifying the frequency content of the record. Sometimes this can lead to some significant changes to your record, which is why a lot of structural engineers are not big fans of tight spectral matching. Because of that, and because of some studies that have been done, I do think we need to do some more studies on this, there is a 10% penalty if you use spectral matching. With mean spectral matching, you're modifying the record slightly such that the average of the spectrum resultant in the suite is equal to the target spectrum. And so you're not doing as much modification, and I'm going to show you with the graphics that you see that, but you're still meeting the code. Right now, with the code, because it's ground motion modification, they're applying the 10% penalty, but I know that for some applications, as you work through with the reviewers, people have managed to just set the alpha factor should be 1. So here's the view of the 2 existing methods that everybody knows about. One is amplitude scaling. So here's your suite of records. Each color represents the maximum component of a record pair. And as you can see, they're scaled such that this red, which is the average, exceeds this target spectrum right here. Now, of course, nowadays, this is an old slide, but I wanted to keep it because it looks good. There is a 10% discount. So all these records can actually go down by 10%. With tight spectral matching, on the other hand, here's what the records look like, where each record pair, the max component, is right on your target spectrum. There is no variability, record to record, nor period to period variability in these ground motion pairs. There is variability between the components, though, and so if you were to plot out the components of all these records, it would all be in that same range, but you're keeping that relationship between the two components. But as you can see, in amplitude scaling, you've got record-to-record variability, as well as keeping these peaks and troughs in your spectrum resultant, as well as in the components themselves. But these are the two methods that are currently existing, and these are the most common ones. In amplitude scaling, it has tons of advantages. You don't have to modify the records. It's very easy. You select the records, you apply the scale factor. Oftentimes the scale factor you applied in your analysis program, so you don't have to worry about it. What's good about amplitude scaling is that you're maintaining the individual characteristics of the records. The characteristic period and the energy content of each record is not modified. And the variability and dispersion between periods and between records is there. It's beautiful because you've got these records that are low here and they're high there, and then you've got these records that are high here and low here. You don't have one record that excites all the periods of at all times. And that's really what the drawback of the tight spectral matching is, but I'll get to that. The peaks and valleys can be beneficial to nonlinear response. If you're at a trough here, it gets interesting because as you have yielding, now your demands actually go up, and that's realistic. They're not going down as they would be if you have a regular spectrum or a modified spectrum. Remember that whatever you have here, then the behavior is different on the other side of the peak, okay? But it's hard to see it because I'm plotting a linear plot. What are the limitations? When using a limited number of records, each record can influence the mean significantly. It's really, really hard to get the mean right on. So if your peer-to-peer structure is here, look at this. You're significant. Yes, you can put in a 10% discount, but it's really hard to get it to match at all periods, especially when you're working with long period structures. Sometimes this point right here is what's forcing you to scale the rest of your spectrum up high. And so it may lead to high energy content at the higher modes, and it's very, very sensitive to record selection when you've got 11 ground motions. I will show you afterwards that when you've got a larger suite of ground motions, then all my arguments and negativity about amplitude scaling goes out the window because you're able to achieve both the mean and the distribution that you want with a larger set of ground motions, which is not really that large. I mean, I'm talking about 40 ground motions. So there's a lot of advantages to amplitude scaling, and the disadvantages go away when you use a larger suite. But then again, until we start using OpenSeas for analyses and we're stuck with Perform, people still want a small number of ground motions. So this is what we got to go with. In amplitude scaling, there's a lot of things you can do. Remember, I told you it's very sensitive to the record. And so you can have a suite where the average is the same. I mean, this average here looks the same, but you can have a suite with this much variability in there, or you can have a suite with a lot less variability. And it's all about how you scale one record with respect to the other. Okay? In this case, it's interesting because they're scaled first to minimize the mean square error for each record, and then the overall scaling of the suite. And here, on the other hand, I scaled them such that they would hit the target spectrum and then they got scaled up. And so it's interesting how just your initial scaling can affect the end results of your suite. Again, when you have a small number of records, scaling in amplitude scaling is very sensitive to your choice. And so, but it's great because it gives you a lot of freedom. There's a lot of different things that you can do with amplitude scaling, and that's how you can tell a good suite from a bad suite. But then again, what's a good suite and what's a bad suite? I mean, maybe this is a good suite because it has that much variability. And until we decide what is the right amount of variability that you need in your records, nobody can judge whether this is better than that. So if your structure can withstand this kind of ground motions, then awesome. But wait a minute, the price that you're paying there, you go, oh, look at all the variability that I have here. Well, but then look at this range. Then again, you know, our structure's in this range right now. Here's an example of what you can achieve with a large suite of ground motions. So here's where I did, this is for the PEER project, and I will show you later a little bit more details on this. But these are all amplitude scale records. I can achieve whatever I want in terms of variability, whether you have a CMS as my target spectrum or not, but I can change the variability if I want to over all the period range, actually. So I have very little variability, or I can have a control. This is a constant variability across all the periods. So amplitude scaling is not so limiting when you have a larger suite of ground motions. Tight spectral matching is tight. Here is your set of ground motions, and this is the average, and each individual record pair. And this is, you know, maybe the ROT D100. So that is your maximum component of each record pair. Wonderful thing to do because you can get into discussions as to whether you should have variability or should not have variability. First of all, it's objective. You get the same spectra, whatever your original ground motions were, right? So it's not sensitive to your selection. It minimizes the amplification of the higher modes. I don't have these crazy peaks that I had in the previous case. It reduces the variability between records, and maybe that's a good thing. And it removes the peaks in the spectrum. And it meets the goal of mean response, and it can be done in 2D as well now. What are the limitations? Well, you've got significant modification of your record, because maybe some of the records started off like this, and now you're doing a lot of modification to these records. You lose your peaks and valleys. The energy is uniform. You don't have, you know, this low and high records. You've got an average of those two. There's no variability or dispersion between periods and between records, and it can, if you look at your modified records, they can appear unrealistic. And scale factors kind of go out the window. The concept of scale factor goes out the window because you do directly your matching. So this is the method that is used when you're doing tight spectral matching. Mean spectral modification, on the other hand, is shown in this graphic right here. Look at this. These all look like they're amplitude scale. But if you look at the average, hey, it looks like these were tightly matched. And so when you're looking at mean spectral modification, you're able to achieve that. And what I'm talking about mean spectral modification is modifying the record such that the average of the spectral response is equal to the target spectrum. And you can do this by modifying the records, but you don't have to modify them as much because you're not squeezing all this variability down to zero. The individual characteristics of the record are kept because you're doing minimal modification. The characteristic period and the energy content stays the same. Here's that record that I showed you before, and here's the record that I showed you before. So those are still there. They were just tweaked a little bit. And interestingly, in the limit, if you have a large suite of records, as I showed you before, when the mean is right on, then you don't have to do the modification anymore because you've achieved the goal, or even the modification ends up being that much smaller. And the peaks and valleys of the individual spectrums are maintained. You minimize the amplification effects of the higher modes. Remember those bumps that we had earlier? Well, they're gone now at these higher frequency points. You can control the variability between records. You can actually control this here, and I'll show you in a graphic later. It reduces the peaks in the spectrum, so it has really softened these peaks here, and it does meet the code and the goal of the mean response. You can also set different target spectra for different directions now. You don't have to just keep the two because you're literally playing with the individual records. And that's kind of what you do in the 2D modification that Norm has developed, and but you can control the dispersion in the response between the records. Okay, so you can control this, and within the components, between the directions, and within the records. And I know a lot of engineering firms are using this because they want to minimize the number of records, but you also want to have as close to your target spectrum as you can for your average of your ground motions. Limitations is a little less known, so sometimes it's hard to get it past certain peer reviewers who haven't seen it. It's not mentioned explicitly in the code, so questions arise on what do we apply? Do we apply the 1.1? Do we apply 0.9? My recommendation is to apply a factor of 1.0 because you're right on the spectrum. Because this is such a smooth spectrum for the average, you don't have to put in that 90% or 10% discount. And I think that would be good enough, and I think it's the appropriate factor. If you compare the average of the three cases, there you are. Here's your amplitude scale that has got these crazy little peaks here because it had to be bumped up here. This one just happens to also have needed to be bumped up right here, but oftentimes it's really this period here that controls and it bumps everything up by an additional percent amount. But if you look at the tight spectral matching and the mean spectral matching, they're right on for the average, and so you really improved your conditions. And oftentimes that results in reducing scale factors. If you compare their methods, when you look at the records themselves, you can see the averages are right on between the tight spectral matching and the mean spectral matching, and the records themselves are right on. I mean, look at these, are plotted even in the same scale, and we do have some of these peaks. They're just not as crazy as those peaks, and interestingly, you're able to maintain these, pulses oftentimes because your modifications are not significant. Interestingly, what I recommend when people have records with pulse, don't even modify the records with a pulse because you're not allowed to touch those, but you can modify the other records to make up for not touching the pulse records. You just have to get in there and do a little bit more control of the individual records, which you can, but you don't have to do it blindly like you do with tight spectral matching. And here's what the modified records look like themselves. You can see minimal changes. There's not such a significant change in your record. Once you've modified the records, you can, especially if you look at the acceleration, you can barely tell the difference between them. If you plot displacements, you could, but which is why I'm showing here accelerations. And you compute the spectrum, and then you meet the code, whether you need to be right on the target spectrum, be above it. Maybe you might need to put in that 10% factor. But you could see that, these records look just like the amplitude scale ones, but a little bit smoother, and on average, you don't have these kinks that you see here. Also, there's additional things you can do because you've got control of these records themselves. If you do kinematic effects where you're reducing your target spectrum, now you've got a better control of your ground motions because you're doing period-specific modification, but you're still keeping your variability. You can control that variability, as I was saying before, by doing an additional step in your computing your factors. Now you can have a large variability or a small variability, which is important when you've got a small set of ground motions. Remember, when you do amplitude scaling with a large suite, it gives you a lot more freedom, and you can bring in additional tools to do with the scaling. But when you've got 11 ground motions, you have to go in and modify the records just a little bit so that you can control this variability. What I wanted to show you now is how do you deal with variability when you have a large suite of ground motions? Well, if we can bump it up to 40 records, life is easy because the whole concept of spectrum matching can go out the window. This is for a project that I was working on for the PEER-CEA project. We just got a report out on this. We were looking at 10 sites, and we needed to develop ground motions for fragility curves, so we had to do this for several periods. And so it's neat because it gives you a really nice suite of ground motions. We had different sets of ground motion targets. We were looking at the UHS as well as the CMS and the CS, where the CS gives you requirements on both the mean and the dispersion of the records. And we use Jack Baker's tool to do that because he's got a really nice tool for selecting and controlling what the target dispersion as well as the mean is. And I will show you the figures. So here it is for what I did initially for just using a UHS. And we had a lot of sites and VS30s and return periods. And so here's a plot here of different return periods. This is using the UHS. You could see that you really get a really good job with 40 gram motions per suite. You do a great job in matching the target. This is, of course, a log, but even if you plot it linearly, you could see that there's a pretty good job with 40 records. And it's got a nice variability. The problem was it was almost too small of a variability. They wanted more variability. Well, that's okay. You can bring that in. With 40 records, you can control all the variability you want. Or you could put no variability. So if you use the CS or the CMS kind of concept, where you scale the records such that they all meet at this point, now you've got variability of 0 at the conditioning period, but then you've got these larger variabilities away from the conditioning period. And so here's the first suite of gram motions where I have minimum variability. So this was, I selected and scaled the records to minimize the MSE. And so here's a really tight suite of gram motions. This was 40 gram motions. Here's an example for one of the return periods. But you see, I've got variability ranging at around 20% in the period range. And that could be too small. Well, when you've got a large suite of gram motions, you can bump that up. Using a CMS with a CS, which is a conditional spectral variability, and using Jack Baker's tool, there you are, that you're actually controlling not just the mean, but also this dispersion here. What I did was, well, wait a minute, if I can use that tool and control the dispersion according to the conditional spectra, what I did is I modified the tool so that I could now use give it a period independent variability of 60%, but you can really change that sigma as much as you want. And you could do this with a CMS or with a UHS. So you can have a suite of gram motions like this where you have very small variability, or you can have a suite of gram motions which a wider variability. And here is for all of them actually how I have a constant variability. My limit was 2 seconds. That's why it goes up here, because I wasn't looking beyond 2 seconds. But you can see you've got 20% in this case, and in this case I've got 60, or you can really give it any number you want. Or when you're dealing with a conditional spectra, this is the kind of variability that you want, and that's why I hit 60, because it was kind of close to that average of the CS there. And so here's when, if you put them all together with all return periods, it kind of shows you that maybe that variability doesn't matter too much for these cases, but the point of it is that when you can do what you want to do when you have a large suite of gram motions, you can just go in with amplitude scaled records, which then again, be careful with the scale factors you choose. And as your library of gram motion grows, it makes things a lot better when you're dealing with certain records and scale factors that you could put constraints on the scale factors and still get a decent suite of gram motions. I wanted to conclude with this slide really just to make the point in the conclusions that variability is just something that we're beginning to grasp. Yes, we can control it. We can do all the mathematics we want, but we need to really figure out an agreement as to what does a variability represent, how do we represent it, and most importantly, how do we quantify it. Thank you. Bye-bye.